Hi there, in this second video exploring ways to help you understand reading quantitative research, I will be focusing on descriptive statistics. Now numbers appear in quantitative research in two guises and it's important to be able to distinguish one from the other. Descriptive statistics will appear in all quantitative research. It is simply the summarizing of findings. It generally includes summarizing the characteristics, i.e. numerical measures, of the participants, and these will of course often be grouped using our idea of the independent variable, as well as summarizing the characteristics of the outcome variables, which we know from the last video are often called the dependent variables. Whilst inferential statistics, on the other hand, is the use of numbers, generally using the language of probability, to draw conclusions on whether we can say our results might have arisen by chance or are in fact a real effect, but more on that later. Okay, so let's focus on descriptive statistics. You see, for any group of measurements, for example looking at height, IQ, blood pressure, you name it, we're going to need at least two values in order to realistically summarize this group of measurements. We're going to need a number that represents the average and a number that represents the spread. So let's take them in turn one at a time. Now the average, confusingly in the textbooks, is sometimes given the name central tendency or location, is a single value that purports to be a representative value of the group. So I have two questions I want to ask. What do we mean by average? What kind of averages are there out there? And which of the averages, given that there is going to be a choice, should I use? To answer the first question, let's start with a simple data set. So I'd like you, without using a calculator, once I show you these numbers, to pause the recording and write down what you think the average of this list of numbers is. Okay, if you think that the only answer is 3, then this following statement must be true. Of course, 3 is a valid average, it's known as the mean, but there are other equally valid averages that you could have calculated and presented instead. Other values were permissible, the value 2, which is the median, and the value 1, which is the mode. Now a quick reminder of how we got there. The mean, the number 3, was obtained by adding those values together, in this case it adds to 21, and dividing by the number of values in the data set. Well, there were 7 values in the data set, as you can see there, so 21 divided by 7 equals 3. To find the median, you arrange the data set in ascending order. I've already done that here, lowest to largest, and then you pick the middle value. Well, as there are 7 values, there is one unique value in the middle, which is the number 2. And finally, the mode simply represents the most common value in the data set. And here there is one clear winner, and that is the number 1. So there are 3 common measures of average: the mean, the median, and the mode. There are others out there, but they would only occur extremely rarely, and therefore these are the only ones I think that you need to be familiar with. And if you feel you need a more detailed refresher on these concepts rather than the quick reminder I have just given, then I would invite you to look at a video I uploaded some time ago. Okay, the question of interest to me as a reader of research is to decide if I agree or disagree with their choice of average. Have they used the average appropriately? Now think back to the last video. We had this concept known as the hierarchy of data types. We had the nominal, ordinal, interval and ratio ways of describing variables. If we have nominal, otherwise known as categorical level variables, this is where we can only have counts in categories like eye colour and hair colour and that kind of thing, then there's only one average open to us, and that is the mode. If on the other hand we have ordinal level data, remember that was where the data has a natural ranking, then we can still use the mode, but there's a more sophisticated measure of average, which is the median. Now I've put an asterisk by that word ordinal because there are very rare occasions when you can use the mean for ordinal level data. I've seen an example in the research where they were designing a pain scale where they presented patients with a line around 10 centimeters long. One end represented no pain, the far end represented excruciating pain, and they invited the participant to put a mark on the line where their pain levels were. In that case, you could have measured it very precisely and therefore you could have used the mean. Usually it will be the median or the mode that you will use for ordinal level data. And there's no distinction between interval and ratio in the case of the average. Remember, interval and ratio were measures that were actual measures of things, what it says on the tin, weight, height, blood pressure, that kind of thing. And now whilst you can still use the mode, and you can, if you wish, use the median, you can use the most sophisticated measure of the average, which is the mean. And it's the most sophisticated because it is the only measure of the average that utilizes every value in the data set. Now the story doesn't end there. In addition to where the variable is on the hierarchy of data types, the choice of average also depends on something called the shape of the distribution, and I will say more about that a little later. Okay, that second value to describe a group beyond the average was the spread, and another word for spread in the literature is dispersion. So again, I have two questions. What is the spread? What are the different types of spread out there? And which measure of spread should I use? Now, there are three common measures of spread. Two of these you should remember from your school days. Now, these three measures are the range, the interquartile range, and the standard deviation. A quick reminder, the range of a data set is simply the difference between the largest value and the smallest value. For the interquartile range, you arrange the data in ascending order and find the median, the middle value. That splits the data set in two, and then you find the median of the upper half, that's called the upper quartile, and then you find the median of the lower half, that's called the lower quartile, and your interquartile range is simply the upper quartile, take away the lower quartile. For the standard deviation, that is the most sophisticated measure of spread, and that is where you utilize each value in the data set in the calculation of spread. I'll just upset you by showing one of the formulas for standard deviation. There is in fact one other, but again, for those who are interested, who wouldn't be, I direct you to another exciting video I uploaded a while back. If the last video didn't cure your insomnia, this one I promise you will. But to answer my key question, when should I use the spread? If I have discrete data, recall from last video, discrete variables meant variables that could only have a fixed value. For example, whole numbers 1, 2, 3, 4. They couldn't have values in between like 1.8, 1.95. Like number of children in a family. How many people voted for a certain political party in the last election. So if we have discrete variables, we can only use the range or a slightly more sophisticated measure, the interquartile range. We tend to use the range if our data is spread nice and evenly, but we might use the interquartile range if we have something called outliers. I'll say more about that in a moment. If on the other hand our data is continuous, remember these are measures like height and weight, where in theory we could measure ever more precisely to ever more decimal places, then we would typically use the standard deviation. However, just as we found with measures of the average, it still depends on the shape of the distribution. And I'm going to talk about that now. In order to explore this idea of distribution, I think it's best done by way of an experiment. So let's imagine we take a coin out and we flick it several times. So this is a fun class experiment. I'm just going to visualize in the video. So I'm going to call one experiment an occasion where I flicked the coin 10 times, and out of those 10 flicks I've counted the number of heads. So my variable is going to be anywhere between 0 and 10 for each experiment. This is known as a random variable because I would not expect every time I run the experiment to get exactly the same value. I might do and I might not. Theoretically, it could be any number between 0 and 10. We would expect it to be around 5 because with a fair coin we expect to get 5 heads and 5 tails. But we wouldn't be surprised if it was a value a little higher, a little lower, or occasionally quite extreme. So I'm going to now produce some simulations where I've carried out, using Excel, a series of randomizations. The first slide is a sample of 10 experiments and each had 10 flicks. Let's see what I found. So here's my 10 experiments and you can see that they are indeed values that are gathered around that number 5. It just so happens that 5 did not do as well as 4 and 6, but that is the nature of random variables. You get something called statistical fluctuations. The sample size of 10 is a very small sample size. So I want to keep going and see if I can get a better idea of the shape of this bar chart, which is another way of describing the distribution as my sample size goes up. So I've rerun the experiment with 20 experiments, sample size of 20, and each time I ran that experiment there were 10 flicks. And so now you can see that lower and higher numbers are starting to appear. There was one occasion, one experiment when I only got 3 heads, and there was one experiment where I got 7 heads. But again, it's clustered around those middle values. Let's keep going. Okay, I'm going to pause there. Even with a sample size of 100, which you would imagine would be a pretty good sample size, we still see that the picture is far from settled. We expect there to be a single peak, a mode, and we'd expect that to be at 5 heads. But here we found with the simulation that at the sample size of 100 on this occasion, 4 was the mode. That's not to say that if I ran it 100 times again, I would still come out with 4. I might come out with 4 or 5 or 6. And with lower probabilities, other values, of course, are possible. There also appears to be a second peak at 6, where 5 is a dip in the middle. But I assure you, this shape still has statistical fluctuations and it is not settled. We can see we had what looks like one experiment where there were 10 heads. There was no experiments with 9 heads and no experiment with 0 or 1 heads. I have to run this simulation a lot more times in order to get a distribution, a shape of my bar chart that I feel can faithfully show the true underlying distribution of this experiment. So I've run the experiment 1,000 times. On 1,000 occasions I flicked that coin 10 times. Now we see what I'm calling the true distribution. Its shape is unimodal, there has a single peak, and this lies as expected at the value of 5 heads. Furthermore, this distribution is symmetric in that it falls away on either side like a reflection through an imaginary middle vertical line. To illustrate this shape of the distribution, I have superimposed what is known as a normal distribution, a common math shape that shows how this could be explored or described further in mathematics. So that red line is what's known as the normal distribution, and very often in textbooks, rather than showing the bar charts or the histograms, what they actually show is this red line. They show the envelope, the overall shape of a distribution, and that is what distributions are about. Distributions are the shape of the underlying distribution which we're trying to get to, and their true characteristic is only really manifested when we have very, very large sample sizes. Now, this idea of a distribution shape applies pretty much to all of quantitative research, and it is used to help describe data, i.e. descriptive statistics, as well as helping to draw conclusions, i.e. inferential statistics, and we'll explore that in a later video. So we have this idea of the sample distribution and its shape, and we've seen that these are very useful in considering descriptive statistics, and these also lie at the very heart of inferential statistics. So we can talk about the distribution of the value of a variable, for example, pupil height, or we could think of this as a probability distribution to help us make predictions. So knowing the distribution of the value of the variable, we could predict with certain probabilities what average height a given group of children might be. This kind of information is useful, for example, in the retail industry, if they're thinking about how much stock to buy for various sizes, for example, of jeans. As alluded to earlier, distributions may or may not be symmetric. We saw examples of non-symmetric distributions when we had small sample size. Let's look at some of the ways of describing unimodal distributions. We can have symmetrical distribution, or we can have what's called non-symmetrical distribution, which is often given the label skewed distribution. Now, for symmetrical distribution, the mean, median, and mode are all the same. The mode, of course, is always that tallest bar, but because of the fact of that idea of the reflecting line, that vertical reflecting line, if you were to work out the median, if you were to work out the mean, they would all lie in exactly the same place. This is only true for symmetric distribution. But if we have a distribution where there is a long tail, here there's a long tail to the right of that mode, that peak, and because that long tail is in the positive direction, we call this positive skew. Now the mean, median and mode are not the same. The mean will be the largest value, the median will be the middle value, and the mode will be the smallest value. It's because there's a lot of data piled up in that tail which shifts the value of the average. Now this is why if we have data with an outlier, that sometimes it is not a good idea to use the mean. For example, if I was looking at salaries in a factory, a lot of people, depending on their hours, will be clustered around that middle section. And then a ever small number of people, managers, higher managers, and the owner will have higher, greater salaries. Their salaries will act as an outlier, which will drag the mean up. So in the case of a factory, I might choose to use the median or the mode. And if the tail lies to the left, in the negative direction, then we call this negative skew. This non-symmetric distribution again has mean, median and mode which are no longer equal to each other, and now the mean is the smallest value, the mode is the largest value, and the median is somewhere in between. Now I promised you in the case of both average and spread that their choice depended on the shape of the distribution as well. So let's add that information into my previous statement. So in the case of the choice of average, if my data is symmetric, then I will usually use the mean. And if my data is non-symmetric, if it is skewed, then I will usually use the median. In the case of the average, let's bring the ideas together that I've presented in two different ways. The idea of consideration of the hierarchy of data types and consideration of skew or non-skew. If I have nominal or categorical data, we know that there's only one average available, and that's still true, and that is the mode. If my data is ordinal, or if it is skewed in some way, then I'll use the median. And if my data is interval and ratio, and of course it has to be symmetric, now we can use the mean. Now these are not rules fixed firmly in stone. I've seen plenty of examples where statisticians, researchers will still use the mean even if their data isn't perfectly symmetric, but this is perhaps something just to be mindful of. If the data is very asymmetric or there is strong reason to believe there are outliers, then you might question whether the choice of mean was appropriate. And to close the loop, thinking about the spread, bringing together our ideas. If my data is discrete and or skewed, then I will use the range or the interquartile range. Again, is an acknowledgement of that potential for outliers that I might bring in the interquartile range. If my data is both continuous and symmetric, then I'll certainly use a standard deviation. And again, I do see examples where this rule is not strictly adhered to, and again I think a certain dollop of common sense has to be applied, but it might be worth commenting on when you critique such papers. Okay, that is the end of part 2. Thank you very much for listening.